You hear me there, Kurt?
I can. And let me just, before you start, let me just remind everyone, if you do have a question, go to the questions drop down and your GoToWebinar toolbar. Just type your question in there, and then I will jump in and ask that question on your behalf. But we want to make sure this is interactive, and if you have questions as you go. And again, the reason we and you'll have a chance to, you'll see at the end of Jacob's presentation, you'll see at the very end of this slide deck that I have, we put these folks information up there multiple times. And the reason for that is if after today or later on today you think about something, you go, oh yeah, I have a question, I really wanted to ask I encourage you to ask the folks who are taking the time to do these presentations for you. And you may have a local valve and hydrant guy that you deal with sometimes. But if you have a question of something you heard in the presentation, I would encourage you to reach out to Ryan. I'd encourage you to reach out to Jacob when he finishes his presentation today, and ask those questions to these folks who have taken their time. They're not getting anything for this. They're just coming to present their products and really the technology to you folks to get your CEU credits. And your PDH credits. So I'd encourage you to ask them, and we'll put their contact information up here a couple of different times and at the very end. So if you think about it, take your phone out, take a picture of the screen, or get a screenshot so you have their information and you reach out to them. So Ryan, Jacob, I'm going to go ahead and mute myself and let you go ahead and get started with your presentation.
Sounds good. Appreciate it, Kurt. Turn my camera off here and kind of get to the presentation here. So greetings, everyone. Hope you all enjoyed Ryan's presentation on gate valves and hydrants. Hopefully you guys learned something from that. Like Kurt said, I'm Jacob McGow. I also go by Jake. Just kind of a little bit of a quick intro myself. Got my feet wet back in 2006 into the water industry with the manufacturer direct. 2010 shifted over to the manufacturer's rep role. So from 2010 to about 2019, I was out in the Rocky Mountain region actually. And then in 2019, I began working here in the Sunshine State with Environmental MD and Florida Valves. So just my role is essentially as a manufacturer's rep, kind of looking over the state of Florida in the principles that we represent and try to get those into the market and help end users, engineers, and everyone in the industry, distributors, contractors, you name it. So today, presentation I'm going to be talking about is managing transients to prolong critical infrastructure, understanding system scenarios with air valves, check valves, and surge mitigation options for water and wastewater systems. It's quite a mouthful. This can be a touchy subject, so hopefully I hit some points and maybe kind of make some sense kind of going forward as we all try to make things better as we build. So I'm going to start out here trying to approach this going into the mindset of the ACT approach. If you guys walk away and try to remember anything at the end of this conversation, kind of the ACT, air valves, check valves, and transients. Got a hand there really focused on the transient portion, just because whether it's potable water or pressurized sewer force mains, it seems like there are a lot of issues out there. And not picking on Florida per se, but it's around the entire U.S. So I'm going to kind of peel into this, peel the curtain back over the next 3 slides, and then we'll go into a little bit more detail. Understanding system scenarios. When we talk about a pump station or a pipeline, whether it's potable water or wastewater, typically we always think about normal operations. What we need to be considering also is worst case scenarios. So potable water and pressurized sewer force mains must be designed around worst case scenarios, which in worst case scenarios under all operating conditions. And I stress that all operating conditions, and this includes pump trip. It is always best to have a computer surge analysis done, as there's quite frankly too many variables within a piping network. We've seen the hand calcs underpredict and we've seen them overpredict. So just something to keep in mind. So where does this take this? Where does this take us? Or maybe better yet, why do we maybe need a surge analysis? Possibly to determine why the pipeline is breaking, maybe for new designs so the pipe doesn't break. or possibly to ensure that the pipeline stays pressurized to meet regulatory requirements. That's obviously on the potable water side of things. So again, painting a picture here, kind of understanding system scenarios, and kind of going through a couple of things here before we really dive into some details. It starts kind of with the pump station here, and we kind of have a little layout. The layout of the pump station, we'll know pump curves and everything. Then we can kind of figure out what the pipeline and profile is. What are the pipe materials? Obviously, there's going to be pipe size with that as well. On the potable water side of things, there's going to be a storage tank levels possibly to be aware of. And then we need to know some operating scenarios. So steady state here is a term. If you want to think of this as maybe normal operation. Inside of a hydraulic model, once the steady state is confirmed, then it can kind of move to the next step at the engineering level. For surge, which in most cases, surge is usually the worst case. And it typically involves a pump trip. So with steady state complete, it's kind of time for a surge. I'm going to start out with the ACT for air valves here. We have a profile here with several air valves on it. And what I want to really kind of just point out is all of these air valves, technically they should be sized correctly. Now, there's usually a critical air valve or two in this system, and I like to point out and ask the question, are your air valves properly sized? So I guess before I get in here, I'm going to stop there on the subject of air, confined space entry and air valve air monitors. Here in Florida, vaults and everything are kind of a little bit scarce, but I think it's a good subject just to kind of go over, throw a little safety in here with confined spaces. If you guys are ever in the field and entering an area where it is considered a confined space area, just make sure to check the air with an proper air monitor before you guys proceed into that confined space area. Air valves, like Ryan said in his previous presentation, he referenced AWWA. Most valves have a standard that all the manufacturers have to conform to and meet those bare minimum standards. One thing that most folks might not actually be familiar with is there's another standard that actually goes along with the air valve AWWA C512 standard, and it's the AWWA M51 manual. And essentially, just to pluck out something specific here, this basically says vacuum venting capacities for all air valve manufacturers states a design basis of 5 psi differential at a 60 degree Fahrenheit and a 0.6 coefficient to come up with the air valve CFM capabilities. So typically these are displayed as a data point, be black and white, or observed as a flow curve from each said manufacturer and what they publish. So one thing to point out, if you guys are looking at the curve of your air valve of choice, whether you guys have county standards or if you guys are looking at APL or maybe even using the engineering standard recommendations, that flow curve, when you look at it, you need to look at the 5 psi mark as far as the differential goes to see where the true CFM figures are at. So sizing air valves, there's a couple of ways to kind of do this. A lot of manufacturers have online tools to kind of go through this. The online tools that actually have a pipeline profile characteristic to it is probably a better approach than you can account for slope. But however, one thing here in Florida, we're quite flat with our topography. So slope is not as prevalent, if you want to say, but there are some areas that obviously have some hills and valleys here. And this is a good starting point for true nominal sized air valves. So one thing I do want to point out too with air valves, flow rate through an orifice. So online, you guys can see this, the toolbox tool. These screenshots here that I put in, they also have an app for the phones. You can essentially figure out airflow rate through an orifice. So this is very important. Just kind of looking at things. I mentioned that air valve or that air temperature, degree Fahrenheit. And what we need to do is figure out a pressure differential across the orifice. If we're going to put some figures in here, we have our primary pressure, atmosphere, and then we have our secondary pressure, 5 psi, less than that. And then essentially what we can do is we have our discharge coefficient of 0.6, and some manufacturers do play around with this a little bit, this discharge coefficient, and you can see your results kind of change as you play around with this if you guys have time later on, if you guys are really curious and want to kind of dive into the details of what you guys have or what you're looking at. But this 0.6, this is also stated in the M51 manual. And like I said, some manufacturers also will play with this. Maybe they'll use a 0.7. And then lastly, we put our diameter of orifice. So, a 2-inch air valve size, let's just say, or a 1-inch, 2-inch, 3-inch, and so on. And as you put your result in, you'll get your airflow rate down here. And this is physically what can pass. This is physically the airflow rate through an orifice in that diameter of an air valve per se, if you want to say. So if we kind of take a look at the cartoons here, this is just a typical detail from a set of plans. But when we look at our pictures here to the right, this is kind of where it gets interesting. And seeing things in the field, it just makes me question a lot of things. So I want to point this out to everyone. We can see our riser pipe, and obviously there's a main of something down here, and I don't know the exact size on this picture, but I do know the size of this setup. And this riser is 6-inch. We got our 6-inch isolation valve, and we supposedly have a 6-inch air valve. However, if we look at the top of this, what's our D-rated factor here? I don't know the exact diameter here, but let's just say that's maybe 1.5 inches. So to me, if we're looking at this, it just reminds me of a straw, essentially, of what we're looking at and the airflow of what we're not going to be able to get through this air valve under a vacuum condition. So when I say normal air valve size does not equal size from some manufacturers, we need to watch out for that. The second picture here we're looking at, I find this very interesting, but I was out in the field, I don't know, let's say a year ago, and I took this picture, and I remembered I took this picture. So in this particular case, we got a 4-inch riser coming up to an air valve, and then we have this piping system. Well, we got a 4-inch riser, and again, maybe that's 1.5 inch diameter out. So we have another D limiting factor here, but furthermore, we have what looks like what is that thing called? That's like an odor control box. So this odor control box is also going to have a D-rated factor to it. So I do know the main size on this one. So we got a 4-inch riser and a 20-inch force main underneath this. The consulting engineer did size the riser correctly, but I don't know what happened. Maybe something happened in the bid docs. Maybe there's an APL that overrides bid docs. I don't truly know, but it's the term nominal size of what I think we're missing here. And ultimately, I got a consent order down here. Working in Florida here for the past 5 years or so, it seems like this term keeps raising up, and I don't know exactly where to pinpoint it, but I definitely think it's a concern to look at the entire system as a whole. So again, kind of sizing. Some manufacturers have kind of some sliding scale rules that are nice to use. I do have another Excel template here that I can share out as well. If any of you guys are interested, feel free to shoot me an email. But the example here that I kind of have laid out, we have an 8-inch diameter pipe that we're working with. We know the flow, so we're sizing based on flow. And then essentially what's going to happen is then we come up with our CFM airflow rate. So that's kind of the critical point. And this is the manual way of doing it. We'll get into another way here in a little bit, but essentially these are good starting points for sizing air valves. So again, kind of getting back to the point of what an engineer designs for does not always meet the design basis for what ends up in the field. So I'm going to flip back here real quick. We're going to take that 105 CFM figure. We're going to plug it in. Just kind of do another secondary check. Okay, what size air valve should we be seeing based on some additional calcs that we can utilize? And here in this case, at that 105, we're coming up with 0.93, and then the lower figures here. So the above figure is for vacuum sizing. The below figure checks exhaust sizing. And essentially, we want to take the higher of the two number. If this landed at, let's say, a 1.3 or something like that, we would just have to round up to the next size. So that would cancel these out and just make that a 2-inch air valve using this method of sizing. So if we were to kind of use these figures here, this 105 CFM, and come over here to this table, and all this table really is identifying is fluid velocity in feet per second. We got 358 and so on for 4 through 16 here shown on the screen for us. And if we were to use that 105 figure, essentially it kind of lands at the 5 feet per second mark for an 8-inch diameter pipe. And then if we wanted to size or design for 3 feet per second for the system, well, then we're kind of limited to even a 10-inch diameter size. So just to kind of put this into perspective of what we just talked about back here, what I said was a 20-inch diameter force main. This 8-inch this 4-inch riser that I mentioned earlier as well, this is properly sized because on a 4-inch at 8 feet per second, we have 1048 CFM that is required if we were designing around max fluid velocity in a pressurized sewer force main. Majority of the flows are designed around between that 3 and 5. So even if we looked at the 5 feet per second mark, we need 655 CFM, which essentially equates to a 3-inch air valve. So we definitely have something in question here to look at with some of the air valves that are out in the field. So kind of taking this a step further and looking a little bit in depth, we kind of went over, a manual way of sizing air valves or a couple of different methods to checking true nominal sized air valves. The ultimate check, however, is to have a surge analysis done, which will essentially tell each node inside of that model where each node is at. You're going to have an air valve tied to it if that node has an air valve on it. And essentially, we're going to be able to see the exact CFM required. So, using a force main as an example here, we can go out into the field. Consulting engineers can also do this, your EORs, and essentially walk or drive the line and figure out where all the air valves are at. Just kind of doing some discovery investigating work. And, we can see right out of the gate on on this particular example that we're looking at, we have nominal sized air valves that are called out, but the inlet outlets are different. And these inlet outlets are quite critical when an engineer or a hydraulic modeler is inputting that data into the model for the surge analysis to be done, because these figures directly affect the outcome of what we're going to see. And again, kind of just referencing, I got a couple of keynotes here, 1, 2, and 3. The first one here, this column filled out with actual observed data from the surge analysis. So this is what we will fill out when a report is completed, essentially identifying exactly what is required versus doing it the manual method within the surge analysis. This number 2 here, air valve capability, that'll come from the manufacturer direct. So then we can kind of compare, hey, what are we getting? Do we see any issues right out of the gate? That's going to be identified here. And then assumed air valve manufacturer and model number, if we know that when we're walking out in the field, we we can also record that data. So just again, if we know we have an issue, and this is an example on a force main, if we know we have an issue on a force main, these are the steps to kind of start the process of identifying what data we're going to need to further investigate this later on. Walking into stages of air valves. So one thing to point out, I'm going to flip back to this other slide that I was just on. Air valve slam can also happen, and really the only way to see air valve slam is within having a surge analysis done. So if we're seeing air valve slam, then the hydraulic modeler then knows to level up, if you want to say, and essentially utilize a 2-stage or a 3-stage air valve. So this next slide here that we're looking at here, if you guys were to Google stages of air valves, you're going to come up with essentially what we're looking at here on the left-hand side. This is literally a screenshot right from Google, and all I did was put stages of air valves. Most folks are most familiar with the three typical styles of air valves. You got your release valve, you got your air vac valve, and your combination air valve. There are other variants of air valves from manufacturers that are out there. I mentioned that 2-stage and 3-stage a little bit ago. So if a hydraulic modeler identifies that air valve slam is happening within the system, then that's where these 2-stage and 3-stage air valves essentially come in. And the air valve essentially is coupled with an anti-surge component, or also known as a surge suppression, or also known as a regulated exhaust device, an RED, from various manufacturers. It just depends on who you're talking to. So again, kind of going back to this 2-stage, 3-stage, the figures in how these are modeled, let's go back to this. If we're just modeling, if a hydraulic modeler is just modeling in standard air valves, they're going to put not the nominal size, but they're going to put the smallest orifice into the analysis software and use that. Now, if they are seeing air slam, then the modeled inlet is going to stay the larger inlet. The modeled outlet will be modeled with a smaller figure to address that air slam event happening within the model, to mitigate that, so when it does get into the field, that issue has been addressed. So that's kind of the term 2-3-stage. I wanted to point that out. I really think kind of going forward here in the years to come, this is going to get a lot more attraction and attention, and ultimately lead to, in Florida here specifically, everything is driven around county or city standards, and then an APL is tied to that. And I think performance-based language is going to have to be added to that to help mitigate and address potential larger issues that may be happening.
Hey, Jay.
So yeah, go ahead.
I'm sorry. Let me. I was trying to find a good time to jump in and ask this without interrupting you. Sorry about that. Kevin Smith, I'm just going to read his point in his question here. He says, we don't size air valves based on the size of the riser, but rather on the size of the force main or transmission pipe. I noticed that you mentioned the riser 4-inch and the required CFM. This should be based on the 20-inch pipe instead, correct?
Yeah, Kevin is correct. Yes.
Okay.
Yep, it's the airflow in the main pipe, correct? Or sorry, it's a fluid velocity or gallons per minute in the main pipe that we're pumping. Yes.
Okay. Very good. Thank you.
Yep. So flipping over to check valves, this is the C in the ACT acronym that I mentioned earlier on. So there's essentially 4 main criteria for check valve selection. Check valves play a role in transients. They can help mitigate, and they can also induce transients with check valve slam. So proper selection of pump discharge check valve is critical in water and wastewater pumping systems. Its primary role is to open for forward flow and close to prevent reversal flow when the pump is off. To avoid check valve slam, which occurs when reversal flow suddenly stops, an automatic valve must close very fast, quickly, or use an oil dashpot device for slow closure. Check valve closing speed is also dependent on system back pressure as well. Now, one thing I will throw in here before I forget to mention it, medium speed is generally or usually typically observed as bad because that's where we will see check valve slam. So kind of getting into the criteria here, cost, head loss, closing speeds, and then fluid compatibility. Costs associated to check valve considerations for a system do come into play. Is it the best thing to base the design around? Probably not. There are a few pictures here. We have the silent check valve, a dual door check valve here. We have the conventional lever and weight or lever and spring check valve. Where my mouse is at here, this is actually beefed up a little bit with an air cushion. And not all air cushions are the same from all conventional lever and weight check valve manufacturers. So that's also something to consider. Then we got a resilient hinge check valve. This can come in two variants, just the resilient hinge, your one moving part inside of the valve. And then it can also come with a stainless steel spring also to this component. So your two internal moving parts. This one's also beefed up a little bit. You got a mechanical indicator. So that is an additional moving part if that was applied to this valve or you see this in the valve in the field. And then on the bottom of this, on the wastewater side of things, this valve can also be used on. It's got a backflow actuator. And then we have our tilted disc check valve variant as well. So not really paying attention to cost here, just really per se putting this in here. The arrows here are the more common check valves that I think we see here in Florida. We got the silent check, the swing check valve, conventional swing check and weight, the resilient hinged. The other variant of this is the resilient hinge with spring, and then a tilted disc check valve. These are, like I said earlier, these are the more common ones that we see. The ones on the bottom here, these are going to be essentially more than likely quarter turn valves or a valve variant with either a cylinder on it. It could be an air or water hydraulically operated, or even an electric actuator tied to it. And essentially these terms for these bottom ones down here are kind of called like a power check. So they can be used as a power check as well as kind of essentially a little control valve to help induce linear flow into the pipelines. I will pick on this ball check valve because I'm just humbly not a fan of this thing. It can wreak havoc to systems. If you guys still do have ball checks out in your systems, 3-inch and larger, I would probably consider looking at getting that thing replaced either in your maintenance budgets or your capital improvements projects. Kurt, I'll let you roll real quick.
Yes, thank you. So we have a poll here. We've got A and B, and if you will, in the questions drop down, you can give me your answer. So which of these two check valves has the higher head loss, A or B? I wish I had the Jeopardy music I could play right now.
Hey, while we're waiting for that, Kurt, I'll tell a little safety story here also.
Okay.
So this slide is on head loss. This isn't a head loss story, but it's a head pressure story. So it's a safety story also. So a few years back, probably 16, 17 years ago, I was at a job site in New Mexico adjusting a large slide gate. And essentially what we had to do, the contractor took this whole thing apart and I had to put it back together and readjust this thing. And this was a very large sluice gate, actually, cast iron sluice gate. and I'd adjust all the wedges. And after we got done adjusting all this and checking it out, essentially we had to pressure test it. So that entailed raising the gate and a little bit, and then immediately closing it just to kind of unwedge and wedge it back in to make sure it was going to seal. Problem is, we had one wedge slip on us. So I'm at the bottom of this containment area, 60 feet deep probably. There's a 40-foot extension ladder going down to a platform, and then another extension ladder leading up to that. I'm standing on the bottom extension ladder, and as we realized one of the wedges slipped, we had this massive blade of water coming in on us. So this is obviously a safety issue or a concern. So luckily I was on the ladder itself and was able to make it out of the way quite quickly. But head pressure is definitely head pressure, and always be aware of your surroundings when you guys are working out in the field.
So on the poll question here, it's overwhelming that A has the higher head loss.
Right. Hopefully a majority of folks are paying attention.
Yeah, that's everybody. That's every single answer we had. I'm gonna also read a quick comment here while we've got a little lull here from Kevin Smith's comment. I've actually seen 36-inch check valves being slammed, siphoned open, then slamming shut with air and not liquid when the air valves are grossly undersized for vacuum protection. The vacuum will suck the check valve open, then the air will come back and slam the check valve shut, even weighted and cushioned. This can be eliminated using air valve that is properly sized for vacuum protection, and that has the fourth function of anti-surge, which reduces the large orifice down to a smaller orifice to slow the air coming back towards the check.
Yeah, so, in those larger systems, I would hope that the engineer of record, consulting engineer, has performed a surge analysis, and, those are the things that can be picked up. Not everything is picked up on everything, and, when you go to a startup or something on a project, things do get recognized and corrected, but that's why there's a startup for most projects. So, yeah, I can see that happening.
Okay.
Where are we at here? So back a level here. The answer to this here was A. Obviously, everyone's correct. With check valves, every check valve has a head loss chart to it. That head loss chart also more than likely have the CV, which consulting engineers utilize to size correctly. So just want to kind of point out the head loss chart here, typical head loss chart per se. Check valve closing speeds. Pause that. So typically manufacturers, using like slam predictions per se, they'll use a 20 feet per second deceleration mark. Every system is different, but if we drew a line on this chart here that we're looking at here and went up from the 20, just kind of use this as a guideline. Again, every system is different, but we see a nice little cluster here. And this cluster here kind of lists out tilted disc check valve, double door check valve, resilient hinged check valve with spring, and a silent check valve. We have our tilted disc check valve here, but a lot of times with this tilted disc here, and that's kind of what we're looking at as well here, the cartoon here or the icon is of a bottom mounted dashpot on this tilted disc check valve, and then we have a top mounted dashpot on this tilted disc check valve. On the bottom mounted dashpot, essentially if you think of a snubber rod, there's going to be a rod when this valve is open that's going to push open. And that rod, essentially when this check valve closes, that rod slows the last 10% of travel of this tilted disc check valve down as it closes. And there are speed controls on the bottom mounted dashpot here, which can be adjusted, from, they say, 1 to 5 seconds. It's usually relatively quick in the field. A majority of the time I see 1 to 2 seconds on these bottom mounted dashpots. Now on the top mounted dashpots, it's a little bit different. This top mounted dashpot is actually physically attached to the disc itself of the tilted disc check valve. So we have full range of controllability on opened and closed, and both of those are adjustable. Typically we see a 5 to 30 second adjustability rate on that. And if a consulting engineer has properly performed a surge analysis in a hydraulic model, we can use those figures when we are out at startup and properly dial this style of check valve in if that is the check valve of choice for that project. So you guys, of all these videos that I play kind of going forward, they don't have any sound, so I'll just kind of narrate a little bit over them a little bit. This first one is fairly quickly. Essentially what we're going to be doing is watching the check valves close. And there's this bottom mounted dashpot on there as well. So it's open now, and you see it closed. So it's probably a second there. So this next video here, we're going to watch 2 videos in series. The pumps are going to start. The flow is going to go obviously through the check valve, and where this pumping system is pumping into is actually going to a hydro tank. And then there's a pressure switch on that hydro tank, which once we get pressurized up, I think in this case it's 80 PSI to that tank, that switch will essentially trip the pump, and then we'll see what happens to the system here. Feet per second there was displayed. Pressure is going to get to 80. And essentially we have silent closure. And there's really no audible slam with the resilient hinge check valve with this spring. And we can kind of see what happened here with the pressure monitoring, measuring at the transient level. And when I say pressure monitoring at the transient level, we're measuring, that device is essentially measuring at 100 samples per second. So it gets a really good resolution. And we can see over static, we really only bumped 20 PSI. So that's a pretty soft closure. The other thing that we want to watch for too, whether we're doing lab tests or field tests, are these closing times. How fast did that check valve close, or how long did it take for that check valve to close? In this case, that resilient hinge check valve with the internal spring closed rather quickly. So we didn't get any pressure spikes here. So this second video here, we're gonna watch same thing. Instead, we're gonna watch this with a conventional lever and weight check valve with an air cushion here, if you guys can see that in this picture here. And again, the flow is gonna go through the check valve into the hydro tank. We got our flow right there in feet per second, and we're gonna hit 80 PSI. See some shaking there in this piping system. So here with that slam over static, we have a 90 PSI over static, and our closure time was a lot longer. What was that first one? I think 2.28, so almost 3 times the closure rate. So selecting the correct check valve for the system that it's going into does play a key role. And last thing on check valves here, just fluid compatibility here. Is the valve going to be going into solids or wastewater, or is it going to be going, into potable water, or maybe even reclaimed water? Just kind of depends on what the application in it is and the media it is going into. So now we're going to jump over to transients, managing transients in a system. So we got a valve here on the screen, and I like to ask the question, can we just use a surge relief valve or a surge anticipator valve on my system, and will my system be fine? The answer to that question is maybe, and we'll dive into that here. So managing transients, pump control. Mitigating transients during a pump startup sometimes involves a pump control valve and is not just reliant on a pump VFD to mitigate transients. VFDs sometimes can be finicky, and sometimes we do want the ability to essentially achieve smooth linear flow into the pipeline to mitigate those startup transients when the pump does first kick on, during normal operation even. Secondly, something to watch out for is maybe sometimes a backup generator can cause a transient issue in the system. I know here in Florida, some stations, pretty much every one of them probably have a backup generator, but how often does that backup generator kick on? And is that backup generator programmed correctly to not induce transients into the pipeline? So hydraulic control valves, I'm not going to lie, these are probably the most fun valve to work on. They can look intimidating at times, but you just have to be the water and figure them out. In this case here, we're looking at talking about transients. We're talking about surge anticipating valves, or maybe just a relief valve. I think this is clearly utilized on a raw water application. But clean water for these two on the left. On the right here, this is a relief valve for a sewage application. Now, one thing to point out to everybody, that these devices are put in place to protect the pump station only. Surge tanks and pressure vessels. So I got a little safety guy here. I'll cover this real quick. These are ASME pressure vessels. You can kind of see on the screen here where my mouse is at. There should be a label on there that addresses and identifies these as ASME pressure vessels when they are out in the field, whether they are used for surge or even pump cycle. They're still an ASME pressure vessel. One thing I will point out, if you guys ever come across one of these or walk up upon one, just make sure that there is a small relief valve on these per boiler code. That relief valve is required because that is a pressure vessel. So also with that little relief valve that I'm mentioning, make sure that there's not an isolation valve between that relief valve and the tank itself. That relief valve should be directly coupled to the water or the pressure connection of that tank, and there should be no means to isolate it. It is there for a true safety point, because these pressure vessels are designed to a PS, what is operating pressure. Second thing too with these vessels, you can see here in the cartoon or picture here, these can get fairly tall. Just general ladder safety, make sure you guys are tying things off if you guys are crawling up or figuring out or doing anything to something high up in the air. So just to kind of run through a couple of things, just to cover the basis. These are all surge tanks. The one here on the left here, this is for potable water. This can be in a horizontal as well as a vertical orientation. The other variant to these, it can be a compressor style, of which we see here in the picture, or it can also be a bladder style. There are pros and cons between both compressor and bladder, but I'll save that for another presentation. If you guys want to know more, feel free to reach out. The next picture here, this is obviously used on a reclaimed water system in the vertical orientation. The third picture here and the fourth picture, these two are used on sewer force mains. And I'll talk about the one in yellow first. Essentially, this, if you guys are looking at this, I would assume you guys would maybe imagine this kind of looks like a giant air valve. And essentially, in a form, it is. The one caveat to this style of tank is we have a large compression zone to work with. Now, there's no bladder and there's no compressor to this tank. So ideally, if this was to be used on a force main, this force main would have to go to atmosphere after every pump shut down to essentially recharge this compression zone. Otherwise, over time, this compression zone will essentially become nothing because all of the air will dissolve into the water and go down the line. So this is a very cost-effective, economical option, but there are some design constraints around it. The fourth picture here, we have a bladder-style wastewater vessel, very similar to what the potable water side or vessel would be designed around. Potable water, the water goes inside of the bladder, the air is on the outside. It's just reversed on the wastewater side of thing. The air goes in the bladder and the sewage goes in the tank. So just a couple of things to point out when you guys are considering or you see one of these in the field. These are surge tanks or pump cycle tanks typically. So managing transients, we just kind of went over some mitigation equipment. So what are we looking for? It's not all about the pump station or the lift station. Everyone needs to be considering the entire system as a whole because we have a whole either distribution, transmission main, or force main system to also consider. Utility departments must be communicating. I think that's key here. Kurt, you want to?
Yeah, so I'll take a little poll here. So your interdepartmental communications there in utilities, give us your rating, 1 being bad and 10 being the best. How well are your departments communicating? Go ahead into the questions section and just give us a number there. 7, 8, 9. Good. These are good numbers. Couple more 9s. We have a 5, a 7, 2 8s, 2 9s, an 8, a 9. Good. Most of these are high numbers.
That's good to hear. Okay, so
a 10. We have a 10.
All right, I want to talk to that one. Cool. That's good to hear too. All right, I see my time here, but I'm gonna kind of breeze through. We got slides to get through, but I'll go through the important parts here. Essentially what we're doing here, again, talking about managing transients, and the key topic here is the head envelope. What we're looking at here is a force main, right? So the blue line is the pipe. We can see during a pump trip, worst case scenario, we have a full vacuum going on into this pipeline. So that's the red line. And, you know, if you were to guess, where do you think this utility might be experiencing pipe breaks? It's probably within this first 3,000 or 4,000 foot of section. Now, you can see there are a few air valves installed on this pipeline because the red line comes up and tips up and touches the pipeline. So we got an air valve here, 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 and here, and so on down the pipe. How do we mitigate this? Well, a relief valve or a surge anticipator valve is not going to be doing anything to this system. Essentially, what we need to do is give energy to the system. So in that case, a surge tank of some sort is required to give energy to the system. And when we do that, and when the hydraulic model and the surge analysis is done properly, we can see that this bigger issue here is mitigated with proper equipment. Okay, this is a nice animation. I will do my best to quickly talk about what's going on here. A lay of the land here with this animation. We can see the pressures all along the top. We can see that this pipeline here is 5,000 foot long. And we have our hydraulic grade line, which is the line in green here. So essentially, this is a pipeline that is drawn up that has no air valves, no surge mitigation equipment to it, and is relatively flat. And here in Florida, everything is relatively flat. So just keep in mind what we're watching here. As you can see, every time that hydraulic grade line obviously goes below the pipe, the pressure in the pipe is negative. When it bottoms out, that's full vacuum. And you can pretty much see that all along this pipeline in this cartoon example with no mitigation equipment, this whole pipeline is going negative and experiencing full vacuum. Now, these black lines inside here that are starting to dance around it per se, that is water column separation happening inside of the pipe. And when that water column separation happens, and then when it rejoins or connects back up, you're going to see the pressure spikes essentially create this massive head envelope way up top up here. So this is why we need to properly design our systems, our piping systems. So I missed it there. Give me a second. Right here. Grab it. It won't let me grab. We'll just watch this play out again. So there's a lot of surge analysis software out there. You guys can see in the very bottom right-hand corner, this is KY Pipe. There's Bentley Hammer, and there's several others. So this second clip here, we have a surge tank now on the system, trying to mitigate that full vacuum. And for the most part, we did a pretty good job. We do still see negative pressures. They're not as bad. Let's see if we can catch one here. So we're getting -7, probably 8 right here. So that's still outside, a little outside of the acceptable level. Typically, this is a force main. So typically force mains, we've seen, depending on pipe materials, that is key here. Systems can be designed on this force main to go down to -5, which is considered acceptable in some cases. It probably more than likely will not be acceptable beyond that. But this is what we look for inside of these. And I should also point out, as I pause this here before I play it, the proper check valve with a surge tank in the system also does play a critical role in what's going on. As you can see here, this is a lever and weight check valve that was modeled in, and we're getting a pretty good slam. And again, when a pump trip happens, the transient moves at the speed of the pipe material. So if it's a metallic pipe, this transient is moving at up to 4,000 feet per second. Now, the solution here and what we ended up doing, obviously we still have the surge tank here. We added a critical air valve here. That was properly selected. And then to get rid of that spike from the check valve slam, from the pressure being put back into the system from the surge tank, we changed that check valve up to a resilient hinged with a stainless steel internal accelerator. So on the potable water side of things, pressure traces, I'll go through 3 scenarios here. When a pump station is hydraulically modeled and put into a surge analysis software, a lot of the times we'll look at what is happening at the pump station via the pressure trace. So worst case, we put the E-stop, we got one pump running, we can see what's happening. However, out in the system, we probably have an issue here in the trouble area. And this particular system had an issue here, and they kept breaking pipes. out in the system. So you can see pressure trace at the pump station, just kind of being a node trace here, using the node trace, and then using a node trace out where their troubled areas were. We can also see they're still having issues. And this is just one pump. So let's say there were multiple pumps that were able to run via SCADA. Now we can kind of see what's happening at the pump station and also happening out in the distribution system. Now, obviously, we're below a 20 PSI mark. So this is below or considered not meeting regulatory requirements. And 2 pumps, obviously, is even worse than the first pump. So again, we can see via the pressure nodes, kind of where we're at and what's going on. Lastly, what do we do to fix this? It did take a surge tank with, again, a resilient hinge check valve with an internal stainless steel spring enclosure for fast closure is what was modeled in. And now you can see we're now meeting that regulatory requirement. So transient monitoring equipment, what if you wanted to actually see what was going on versus just maybe relying or believing the surge analysis? There are ways to do this with deploying field equipment. Obviously, what you can see here is we have hydrant options, or there are hydrant options out in the market. We can also field deploy at the pump station devices, or maybe out in the field and just tap the pipe or hook up to an air valve and maybe put that component on the air valve assembly, or maybe hide it in a meter box. And the same thing too goes for monitoring pressures at a lift station. We can also figure out what's going on or further diagnose what is going on at a lift station. The key here is 100 samples per second is the benchmark. It's a good minimum to get a good resolution to see that transient, to see those transient pressures. Yes, there are manufacturers that do go way higher, but you're going way higher, and a lot of these components are installed out in the field, and all you're doing essentially is killing your battery in the long run quicker. So it does require more runs to the field with your folks. So model calibration and network calming, using a force main as an example here, we can kind of see what's going on here. This is high resolution data captured, and this is normal operation. So you can see here, we got a full -9 on this example of a screenshot, and then we can see the wave speeds. And when we have good resolution and wave speeds, we can essentially help calibrate a model and dial in the pressure trace to what we're seeing under normal operations, and then go to worst case, which is pump failure or power loss at a pump station. Now, believe it or not, this -9, this is not the first time I've captured a -9 from field data here in Florida. Network calming kind of is the key here on this next slide. Triangulation is, I think, a really powerful tool. And with multiple units deployed, essentially with high frequency and clock accuracy, we get really good resolution. And with that, and tied with GIS data, we can essentially, with the software running in the background, land a flag and say, your transient was likely induced from this location. Now, this is not AI, but there are algorithms running in the background, working and doing this work for utilities to help further diagnose. So it's essentially kind of like a second set of eyes on your system running in the background. To deploy these studies or projects, obviously we need to do a deployment plan, and we can do those on transmission mains and distribution systems as well. Leak detection also comes into play, supporting those water loss programs. The non-revenue water, obviously, everybody's trying to maybe figure that out. The technology's here. The device is at the edge to help engage with your network. It's like a radar for your pipes. So just kind of putting that out there. If you guys want to learn more, feel free to reach out. Kind of wrapping this up here, painting the picture. We have GIS data. Great. If we don't have GIS data, then we can just go to Google Earth, We can draw things out in Google Earth to help us get to a steady state model or help produce a steady state model, which in turn helps us run that surge analysis component. I mentioned non-riverine water earlier. Just Googling around pipe breaks, what I really want to point out here is on the water side, 240,000 water main breaks every year. Sewer really isn't recorded at the national level. However, there are obviously quite a few sewer breaks. But when we step outside of our industry from the water, wastewater, and we look over at the oil industry, now granted this data is from 1986, they state 300, on average, 300 breaks per year. There's a huge gap here in what's going on. So what are they doing and what are we not doing in our systems? I think that's the question, and I think that's maybe something that we all might want to take a peek at. Lastly, there was a good abstract from ACE 18. If you guys would like a copy of this, I am happy to share this. Dr. Robert Lashir did a pretty good abstract on this. Essentially, it dials down and sums up in the first 2 pages, but it does have a lot to do with microfractures, and microfractures are caused by water hammer. There are other things too that go along with this, but that's the leading thing that really sticks out. This is a great intro here. We do have a nice example here just how to do a surge analysis. If you guys have a city engineer or a consulting engineer that may be interested, happy to share this as well. And as always, I do hope you guys all continue to educate, constant learn. And this is not an easy button, but we do need to act now on air valves, check valves, and transients. And everyone's best work is yet to come. Any questions?